So we just finished up with direct and set associativity. Does anybody have any questions on that based on their assignments before? Are you missing a page from your homework?
Somebody else.
Oh, okay. Thomas, you had your assignment. All right, does anybody have any questions on direct and set associativity? All right. So for the rest of section 6, we're going to talk about this concept of virtual memory. So up to this point, we've dealt with local registers and data memory, and now we've dealt with this cache hierarchy, and that's cache hierarchy. We're dealing with this main memory idea. So now we then deal with disks, where we have the non-volatile memory. And we're going to be talking about how we interact between this main memory and this non-volatile memory. Now, virtual memory is this concept where we're kind of having the same interactions between the non-volatile memory and the main memory as we're having between the main memory and the cache. So in cache, we call that cache hits and cache misses. We're going to call that page hit and page miss. And so what happens here, we talk about these 4 gigabyte computers now that have these large programs that we can run. So in the program that you're going to be using in your final project, you're going to have this small program that has a main and it has one function that it calls and it runs it based on what we're going to be learning about in section 7. But now, if your main memory can only hold a certain portion of the program, how are you going to be able to actually execute the whole program? You're going to be swapping pages back and forth to go into your main memory, and then the main memory is going to take advantage of your principles of locality, your temporal and spatial locality, to be able to improve performance. So, well, let's say since you have 32 possible memory addresses, you could represent 4 gigabytes of information. How do you translate that into potential memory locations if you only have 16 kilobytes of actual main memory? And so that's how we're going to define this concept of virtual memory. So virtual memory is a technique that uses main memory as, in quotes, a cache for secondary storage. So we have this non-volatile memory, and we're swapping it back and forth into the main memory, and the main memory is the cache. So when you run programs on Java and you use the Java virtual machine, you will notice, especially how many of you use VMs on your computer, like you're running a different operating system, a VM? Okay, so a couple, right? And you notice that when you actually run the VM, it's actually running really slowly. The reason why is because it's running in virtual memory, and instead of performing those swaps in the cache, where you're doing cache blocks, you're actually using pages back and forth. However, that takes a lot more memory, and it has to go a lot, so it ends up going a lot slower. But the advantage is you don't have to deal with the computer architecture. You're actually that the Java virtual machine will compile down there for you. So the reason why, there's 2 main reasons why we want to be able to use this. We want to allow for efficient and safe sharing of memory among multiple programs. So instead of just one program like we were using all the way back when Kernighan and Ritchie were programming in B, now we're doing C, now we're trying to do Java where we have this virtual memory. Now, the second is to remove the programming burdens of a small, limited amount of main memory. So what I've taught you in C is how to be able to compile down to the machine code to be able to manipulate the main memory so you understand the underlying advanced digital system. So now, before we actually get into the processor, I want to show you this virtual memory, kind of show you the differences between what you've learned previously in Java and what you learned in this course. And so what you guys did, and the number 2 is the reason why you guys were taking Java in your previous coding classes. So you have to really deal with a lot of pointers. You have to deal with garbage collection. You have to deal with memory allocation and all that stuff. But as electrical engineers, it's very important for you to know. So those are the main motivations for using virtual memory. And it was actually proposed by a PhD student, this concept of virtual memory. It's Rudolf Gunst. And basically, it's called local design of a digital computer with multiple asynchronous rotating drums. So that's the key portion, is this rotating drums. And the whole point is nowadays in your computer, you're using RAID arrays to perform these operations. But back then, you had these larger disks and tape and drums in order to ensure you're moving the information back and forth from the drums and now RAID arrays to be able to get here. So we have to talk about programming address space because that is how we actually use the information here. So an address space is a separate range of memory locations accessible to only one specific program. So here's what that means. We have some, why is that, what's going on here? There we go. So we have a set of addresses of main memory, right? And so the address, and we have this smaller, so we do this cache hierarchy. Remember that diagram I showed you a couple classes ago where you start with, you have your microprocessor and your registers, and then you deal with level 1 cache and level 2 cache, and then you deal with main memory, and now you have this non-volatile memory. And so there's a point where a certain amount of it is going to be used for a specific program. And this physical address, which we'll define here in a second, is where it actually is in the main memory. So here we're going to be talking about the conversion between a virtual address and a physical address. We're going to be doing an example problem with that. And so we're going to be, the processor, which we're going to be learning about in section 7, is going to issue a virtual memory address, and it's going to be converted to a physical address in what's known as a memory management unit. And then it's going to go here and get this information through direct memory access, and then it's going to come back and be able to update all the levels of cache hierarchy. So that's the difference between the program's address space and its physical address, which is the physical location in main memory of the program. Forgive me, I know that says end 8.5. That should be 6.22. So how do we get this back and forth? We use what's known as a page. A page we formally define as a fixed length contiguous block. And the reason, before I go further in the definition, the reason why it's important that it's contiguous is in the concept of an operating system, there's two concepts of paging and segmentation. So paging is like a cache block. We have a specific contiguous block of information that we can pass back and forth. So you might be able to get the whole program in the page. You might not be able to get the whole program in the page. In segmentation, so if we say this is a page, and if this much is the program, then we put in the whole program into the main memory hierarchy. However, let's say we use this concept of segmentation. So here, we would only, if we had this much, we would only put in that amount and then swap that amount out. But then, so there's pros and cons. You're using less memory from segmentation. However, you suddenly have all these little blocks of memory all over the place that get taken up. So if you don't properly allocate it, it becomes harder and harder for the operating system to find a place to put your program, which is why when you leave your computer on for out, you have your pointers going on, and then you have all these little segments going all over the place. So that's why you have to be very careful about memory allocation, which is why I'm so adamant about it on your coding assignment. So that's where a good advanced digital system designer accounts for these things. And so, to continue the definition, a page is a fixed length contiguous block of virtual memory. It is the smallest unit of data for transfers between the main memory and the non-volatile storage. And ignore the 8.5. So, what is its equivalent in cache? So we had all these definitions for cache, right? So we talked about page. In cache, what's kind of the equivalent of the smallest amount you can transfer back and forth? A block. Correct. Very good. Very good. So in virtual memory, its equivalent is a page. And you probably could see that because I have the little note. I didn't even read it, but the little note here, it says similar to a block. Okay, so I'm going to go past physical address and go here, 6.23 with virtual memory. So as I described a little earlier, the processor is going to issue a virtual address. It's going to be converted to a physical address in main memory. kind of like how you have you think about in cache, you have the pointer is generated to generate your load word address, but then you're dealing with cache and the load word deals with your index, but then you have the tag, and the tag allows you to communicate back and forth, and you have the number of tags is the number of potential blocks you can transfer back and forth. Same thing here. We're going to be dealing with virtual address and page offsets. So virtual address we define as an address that corresponds to a location in the virtual memory. And we'll have all of a diagram that we'll show. We'll go to example question and a diagram that goes into a tremendous amount of detail about this relationship between virtual address and physical address. And so the page offset is equivalent to the tag, and it's equivalent to the page size. And then the next one is virtual page number. And so our page offset is determined by the actual page size here, log2, kind of just like set or block size, right? And then the virtual page number is determined by the address size minus the page offset. And in the next example question, it'll make this definition more intuitive. But the whole idea is that you have this whole potential address space, and then you have, so let's say 32 emits, right? And your page size is, let's say it's 4096, right? So that means it's 2 to the 12. Yes, 2 to the 12. So you have 12 minus 32, it becomes 20. So that becomes your virtual page number. And then the physical page number is determined by log2 of physical size. So log2 of 2 to the 32 is your physical size. So your physical page number translates to virtual page number. So you're able to use that information to translate how many pages you can possibly have in the virtual space and the block, not the page. And by using that, you're doing the same translation that we did last time with cache blocks and main memory. So we have a diagram, an example question, and then 2 more diagrams in this section that I'll tie everything we just talked about here together. And so I'm going to scroll up past 23 and 24, and I'm going to try to zoom in here a little. That's a little too much. I want people in the back to be able to see 25 and 26. Okay, so we have this virtual memory system. And so this is what I was describing to you earlier. So the processor is going to do a calculation with the arithmetic logic unit, and it's going to calculate what's known as the virtual address, sometimes also known as the logical address. And this goes to the memory management unit, which we're going to be doing an example question of how the memory management unit, right here, example 6.9, translates the virtual address to the physical address. So when you get your physical address, you have to check a number of things. First, you have to see, is that information actually in the cache? Because you recall in virtual memory, we do this page swap, and then we update the main memory, and we update the cache levels based on temporal and spatial locality, right? So we're going to do the same thing. The first thing we do is we're going to check to see if it's in cache. If it's there, we just go right back to the processor. If not, we have to actually go to the main memory and perform our level 1, level 2, and level 3 swaps, right, with blocks. And then we translate this physical address back, and if it's there, we transfer the data back and forth, which then goes back to the processor, right? I use the pen here to kind of describe. So we issue the virtual address, which we're going to describe in this example question here. Memory management unit will convert it to a physical address. So now we know where it physically is in memory. First, we check the cache. If it's in cache, then we just go back to data, right? Put it in there and we do a process. So let's say it's not there. So now we go to level 1. we go to level 1, check main memory. If it's there, we send it back. 2, we have to go to level 2, just like we talked about before. And then we do memory and data translation and update our cache and perform the operation like we did before. So now, the rest of the diagram, when we're talking about direct memory access, is what happens when we deal with the virtual memory. So we have this physical address, we go into main memory, it's out there, then we go into the disk. So we go to our disk using this concept of direct memory access, where we use the physical address to get the value to tell us which page is there. So if we find the page that we want in the disk, and then with the disk, we put a page in, we take a page out. There are a number of algorithms that are used to determine a proper page, but for this course, we'll just stick with least recently used. So we have the least recently used page put back into the disks. We bring in a page here, and then we update main memory. We update our levels of cache, and then what's going to happen is the value that we want is going to be in level 1. We put that in the processor, and then we perform our operation. Okay. Does what I said make any sense? Okay, getting a lot of head nods. That's a good sign. I like that. All right, so let me erase all of this. All right, so just do that. Okay, so we're going to do this example 6.9. Give you a hint. You can expect to do something like this on an exam. So now we're given a 32-bit mixed data path, right? So the page is set at 4 kilobytes. So what does 4 kilobytes mean? 4096, very good. So let me write this up here, 4096. So 4,000. So using our definition we had from a couple TGOs ago, what does that mean our page size is going to be? Our page number. What's the equation we use? Actually, let me move over here so you all can actually see. So 496 log base 2. Log base 2, right? And what's log base 2 of 496? 12. 12. Very good. So that's our first step that we've done. Log 4296 is 12. The first 12 bits, so when we come up with this virtual address, 11 down to 0, are the page offset. So that's where the definition comes into play. I'm going to, does everybody have this drawing? Okay, good. So I'll move past the drawing so everybody in the back can see as well. All right, so this is how this memory management works. So the first 12 bits from 11 to 0, so in the solution that we have down here, that's our page offset, right? We calculate that by taking the page size, doing log base 2, and getting 12. So those are the 12 least significant bits of our virtual address. And so the virtual page number, we just use that since we have 32 bits. 32 minus 12 is 20. Because if you recall from, I'm going to scroll back to a previous TGO. Recall this 32 minus 20? That ties into this definition 6.25 of the virtual page number is determined by the address size, which in our case is 32, minus page offset, which was 12. So that becomes 20. And so here's what we're doing. So we have 20 here, and these are the next 20 bits. That becomes our virtual page number. Now, the last thing we have to do is deal with the physical number of physical pages. The number of physical pages as stated in the problem allowed is 2 to the 18. So what does this mean? we're actually having a translation between this log 2 to the 18. In that case, it's very simple. It's just 18. So to come up with the physical address, we have a translation between our 20 bits here and the 18 bits here. So what this virtual address means is that we could potentially have up to 2 to the 32 bits of memory space. We have said that we have 2 to the 18 number of physical pages in memory. So that means we have a translation between what is in our virtual address as issued by the processor and the number of pages and which page I want. And so this is how that memory management unit is done. So let me scroll up here, kind of walk through it again. So here's how everything works as the problem is stated. So we're given a 32-bit MIPS data path, just like we have done all semester. The page size is 4 kilobytes. So first thing you do, get my page offset. The page size corresponds to the least significant bits of the virtual address. That's how we get this. It also corresponds to the least significant bits of the physical address. So now we use the difference to calculate the rest of our virtual page number. So there's going to be a number in here, which the next diagram, I believe, will make clear this translation. But that becomes 20 bits. Now, the second part of the problem states the number of physical pages allowed in memory is 2 to the 18. So I have 2 to the 20 potential pages that I could calculate in the virtual address and 2 to the 18 actual pages. So there's some sort of translation going on here. Now, it's not as straightforward as just saying, well, why don't you just make the 2 to the 18 least significant bits of the virtual page translate to the physical page? Now, why do you think that wouldn't be the case?
You might have some important things in the
Okay. What's the word that starts with L that ties into that idea that I've said 3 times today? I'm not global, I'm locality, right? That's one of the 2 issues. What's the other issue?
It's not 32 bits.
Well, all right, it's not 32 bits. Well, let's say, so I have 20 here and I have 18 here. What's stopping me from just lopping off those 2 and just using that to directly correlate? What's happening every time I need a new page? Okay, so I have this, I'm swapping it. So I'm putting it in there and I'm putting the previous one back in its old spot. So now I have to use these pages back and forth. So the pages move around. So what's going to happen here, and that's where this next diagram is going to tie into play, we're going to use this page table that tells me where everything should be in physical memory and then other locations in the disk. So that is why you can't just match those back and forth. Now, to improve performance of this virtual memory, we're going to use something what's known as a transition look-aside buffer. And so this you can definitely expect on your exam right here, if it ever draws. There we go. So a transition look-aside buffer, which is actually this part of the diagram, is its own separate cache that keeps track of recently used address mappings to try to avoid access to the page table. So what does that mean? Our page table, so we have our virtual page number, which we calculated in the previous problem, what we need to do. So then the first thing I'm going to do is I'm going to go here and say, do I have a local cache which actually contains that physical page that I'm looking for? So I have some valid bits and a reference bit, right? So what that means is, is this value being used by something? And you can see, if you look at these values, 1, 2, 3, 4, and 5, and then you have 1, 2, 3, 4, and 5. Which ones are being used? So it's actually being used, so it's a valid bit. and then the reference bit, again, is it actually being referenced to a physical page? And then dirty bit, has it been changed? Have we actually changed the value since we've swapped it in from physical memory? So the dirty bit, what that means is the copy of the values here in the transition look-aside buffer, are they different than what's in the physical memory? And then ultimately what's in disk storage? Because if you, let's say you have a Word document, you're writing a report for project 2, right? And you're doing all your work, and everything you're updating is here in the TLB and your physical memory, but you're like, you know what, I'm done for today. I'm not working on this anymore, or I got another assignment I need to do. I'm turning my computer off and I'm doing something else. Well, you need to be able to go through and say, have I actually properly updated the Word file, right? So what's happening is, it goes through and says, okay, these are dirty. That means you've actually saved the file, and before you turn your computer off, I'm going to store it to the disk. So that way, when you turn it on, you don't go, oh my God, where's all my write-up? Dr. Morrison's going to give me an F, and I'm going to fail, and I'm going to hate my life. That's what this dirty bit is doing. That's the whole purpose of that. So here's what's happening in the transition, what's going on here. So the virtual page number is issued by the processor. The first thing it does is it checks the transition look-aside buffer to see if the thing that it's looking for is there. The short cache, if it's there, sends it back. Okay. If it's not there, it's also going to check the page table, which corresponds to which page in the disk storage corresponds to the location in physical memory. So you see how they're all kind of in different orders right here in the drawing? And by the way, when you do the exam, I don't need them to be exactly as drawn here. You just need to demonstrate that you understand that if there's a location in the page table, it will correlate to something in physical memory. And the fact that you can just draw it anywhere is fine on an exam, as long as there's lines. And the reason why is because of that swapping that we were just talking about. It'll swap, it tells me this, so if I have this value, valid bit, okay, so if you see how there's nothing here, there's no valid bit, it is corresponding to a page, but there's nothing here. So let's say I needed this, I swap it in, then I update the valid bit, and then I update the page table because of data physical memory. So what happens is I go to the page table, I find the translation, which is that little block in the previous problem, and then I go to the specific place in physical memory. It's most recently used, so I'm going to update that, and I'm going to update the transition look-aside buffer, and then put that in my cache hierarchy. Does that make sense? So what happens is if I'm done with something, if I have a full physical memory, and I need to bring in something from disk, the disk will first go to the page table. It'll find the least recently used bit for reference. It'll say, this is my least recently used page in physical memory. So what's going to happen is it's going to take it out and put it back in disk storage. Then it's going to take the one I want, use that page table, put the actual page in the physical memory, update the page table, update the transition look-aside buffer, and then go back into the cache. Does what I just said make sense? If it doesn't, do not be afraid. I will gladly address any issue in this. Okay. All right, so the last part of section 6 are this definition and this drawing that kind of emphasizes a little more of what I was talking about. So a page fault is what happens when an access page you're looking for is not in the main memory. So to kind of go back to this, I want something, it's not there. I go to the page table, it's not there. It's not in the physical memory. It's like a cache miss. We call that a page fault. So let me formally define it again. an event that occurs when an access page is not present in main memory. And so this drawing, we're going to talk about what happens when we have a page fault, sorry. So all the data is organized in pages. So you have an approximate number of pages here. So we have these disks. And so the disk information, so if you have a page here, you're going to write it to main memory, like we talked about previously here. And so the way that, and so it's accessed by physical addresses. So you issue a virtual address from your processor. It comes to this main memory management unit, which deals with the processor cache. If it's not there in cache, it then goes to main memory. Main memory, it looks at your transition look-aside buffer. If it's not there, it put in its own copy of the cache. It looks in the page table to look in my local pages in the main memory, the physical memory. If it's not in the main memory, that's a page fault, and then I have to write back and forth between the pages here and the disks. So all the data is ultimately organized here because you want to be saved when you turn the computer off. And so we say a page fault is a required page is not found in main memory. Cache miss or required block is not found in the cache. TLB miss is a required virtual address is not found there. So if you include this entire diagram, we've included, so by including these two diagrams on the exam, you've demonstrated to me that you can show how a virtual page is addressed, show virtual data and reference bits, how the transition look-aside buffer correlates to a page table, how it correlates back and forth with virtual memory and disk storage. Here, for 6.30, you know how the disk works, you know how it's organized. You show how the interaction with this concept of write back, which we'll actually go into more detail in section 8. How do cache pages and page table work in main memory? You'll properly define page fault, TLB miss, and cache miss in the memory management unit. So if you can put in these two diagrams on your exam with those definitions as stated in 6.30, you've demonstrated quite a bit of knowledge. So I will leave this here. This is where exam 2 ends. So let's have an exam review right now. The exam is a week from Thursday. So you have the opportunity to do your TGO assignments, turn them back in, they get handed back to you on Tuesday, and the exam is next Thursday. And if you recall, the coding assignment is due on Sunday. So I posted all the section 4, section 5, section 6. As you probably could see for those groups that have already started working on it, it just builds on each other. And this one will be worth 75 points. So if you correct everything from assignment 1 that you might have gotten wrong and get it working, and get project 2 working, it then contributes to the score. So that's where the scaling up of project scores helps you. So if your group didn't do that well on project 1, it's easy to rebound. Right. So exam review. So what do you think will be on the exam? Okay, so yeah, so these diagrams, I'm going through and checking them just to make sure I get everything that. Okay, so this diagram. What other diagram did I say today? The one above it, right? Making sure you guys hit all points. So what else?
Division or restore division.
Yeah. Mm-hmm. So that's where it started. Restoring or non-restoring division. I'm going to give you a problem. You have to state which algorithm you're going to use, and you have to do it properly. What else?
Average memory access time.
Average memory access time. Very good. What else? Assembly code.
Machine code.
For the benefit of time, I will not require you to do machine code. On project 3 and project 4, you'll be doing machine code with the actual coding. So, what else?
Memory versus registers and MIPS.
Correct. What specifically about, and then specifically there's that, and then there was another thing involving memory.
Locality.
Okay, temporal spatial locality will be on the exam. Very good. That will be on there.
Transition looks like buffer.
That was in the diagram. Yeah, you did say that.
The register types.
Okay, the register types. There's the 3 types of registers from the quiz, right? And so what was the other thing that I harped on from memory? So there's memory versus registers, and then there's one other thing from that section that I really wanted you to. There's 5 of something.
The functions or the
It's on the tip of your tongue, isn't it? Not functions.
shift.
Well, shift them out is in.
Are you talking about the point?
No, that was what he just Austin just said a little earlier. The 3 types of. The 5 types of what? Of what? Yeah, the 5 types of memory addressing. That would be on there. That was what was on the tip of your tongue, wasn't it? So there's 2 other big things that you guys have missed.
Shannon expansion.
Shannon expansion. Actually, well, that's 3. So Shannon expansion. Yeah, you did that. Shannon expansion. Once you practice that, it shouldn't take long. So there's 2 other short problems. One we covered today and one we covered last class.
Example 6.9.
6.9. What is example 6.9? What is that? What is that concept asked about in there? Virtual memory translation to physical memory. And so once you understand logs, it's just you draw it out. It shouldn't take you more than a couple minutes. And then what was the big thing we went over last lecture? What was that last big problem that you guys submitted today? Direct and set associative, right? So I give you a cache hierarchy with some number of words, cache access time and a memory access time, and then you show me the interactions between if it's directly mapped and set associative, and then you compare the performance. So did you guys miss anything? Extra credit question, Nope, you guys did everything. So, like I said, at the beginning of the semester, when you do the exam reviews, you guys will be able to make your own exam review. Okay, so let's start getting into section 7. This TGO assignment and Thursday TGO assignment will be due next Tuesday. You won't be submitting it because I want you to focus on exam study. All right, so I've been alluding to this processor thing for a long time, haven't I? So this MIPS data path. We're going to be going over all the stages, and by the end, we're going to have a full data path constructed and built. So we have the ALU, we've got our registers, we have our instruction memory, we have our data memory, we have controllers, we know how to shift left logical, we know how to do 64 to 32 multiplexers, we know how to do control units. You designed the controller and the ALU controller previously. Now we're going to put all these pieces together. So, instruction fetch. We have this idea of a program counter. We have this idea of a program counter here, where it actually points to the specific program. The specific instruction that we're going to be needing. So we start at instruction 1, right? And we use this byte addressing, so it's actually the value that's coming out is going to be a 4. So we have 4, 8, 12, and so on instruction memory. And then here we get that value of the instruction, and then we hard code add 4 into a 32-bit adder. and then the value comes out, and we're going to show other stuff for the purposes of this stage. It would just immediately update the program counter. So this value that comes out of the program counter is known as the read address. This tells me which address I want to read. Since we're using byte addressing, I get that one plus the next 3, combine it into a 32-bit output into the instruction memory, and then the instruction comes out. Okay. So that's instruction fetch stage. So when you begin programming assignment 3, the first thing you're going to do is you're going to take that instruction memory that you had that you're working on for this project. You're taking some sort of input. You're going to take your 32-bit adder, which you designed, hard code 4, the 32-bit value 4, plus the value that comes out, and you just code this and put all the pieces together, and you've got problem 1 done. So in your description, you just say, oh, we call it instruction memory this, we call it a program counter this, we call it our adder this, and we put it together and it works. Okay, so does this make sense so far? Right. So instruction decode. Now we have this 32-bit value that's coming out, and now we're going to talk in an incredible amount of detail about how we are able to differentiate between an R-type and an I-type and a J-type instruction. That comes in this stage. So the first 6 bits, as you guys know by now, is the controller. 25 to 21 is used in both R-type and I-type instructions, so they're going to go immediately to the register. It's a 5-bit input, and we have how many registers in MIPS? 32, right? So if I have a 5-bit value and I want to select one of 32 values, how would I convert that? By 5 inputs and 32 outputs. Starts with a D, decoder, right? And so you're doing a 5 to 32 decoder in this coding assignment, right? So you just take what you've done in your previous coding assignment, you take those 5-bit inputs, and you take those 32 outputs, and you tie that in a for loop to each bit. So if you have that bit value and that corresponds to your reg write, that's how you actually get the specific value that you want to read for that register. So then you have to make this decision between R-type. We have 20 to 16 for RT, right? And RT for I-type, for I-type it was 20 to 16. And for R-type, what are the bit values for RT? You have to make a decision between 20 to 16 and 15 to 11, right? Because if you recall from your R-type instruction, you have your opcode, which is 31 to 26, then RS is 25 to 21, and then RT is 20 to 16, and then RD is 15 to 11. And then you have an I-type where you have your opcode, and RS is your input, and then RT is your destination register. So this was 20 to 16, and then 15 to 0 is your immediate. I'm giving you a solution to an exam question, right? You have to make a decision here on which value is going to be going into to the destination register. And the destination register is writing. So if I was designing which register you wanted to write, and you had to make that decision, how would you do it? As engineers, what would you do? I have 2 5-bit inputs, and I want 1 5-bit output to select a 32-bit value. Use a multiplexer. And so if I'm deciding which register I want to write to, what would you call your controller of that multiplexer? If you want to make it a simple name, if you wanted somebody who saw your code in the future, and you wanted to know that you were writing to the register using this control signal, what would you call your
control signal register?
register. What are you doing to the register? Writing. So you just call it register write, correct? It's that simple, right? So you have this control signal, reg write, which controls two 5-bit inputs for multiplexer with one control signal, one 5-bit output. Then it goes to your 5 to 32 decoder, and that value, when you go through your write stage, will allow you to tell you which one you want to write to or not. And so, TGO 5.2, I'm going to go through and we're going to define all the control signals. It is in fact called register write. It is used to indicate if a register is being written to or not. If 1, then a register is being written to. If 0, no register is being written to. And then register destination tells me which one I want. It's used to determine if the RT or RD register is being directed to the right register. Write, W-R-I-T-E, not write, R-I-G-H-T. So the controls a 10 to 5 multiplexer, like you guys designed. If it's 0, then it's an I-type instruction. And that sends 20 to 16. And if it's 1, that means it's an R-type instruction, and that sends instruction 1511 to the right register. So here's what we have. We have registers. We have reg write up here, indicating we want to write to the register. And then 25 to 21 is automatically always being sent to read reg 1. And so we're going to always send 20 to 16 to read reg 2. But then, based on the control signals, we may not necessarily read it because it's an I-type value. But then we also split off this value here. And then we have 15 to 11 coming here. And we use a multiplexer. And that value is controlled by register destination. So then we have a 5-bit output, and here you have your decoders to select the specific value, and so on. And so I will formally define register destination. It's used to determine if the RT or RD register is being directed to the right register. It controls a multiplexer. If it's 0, it is then an I-type instruction, and instruction 2016 is sent to the right register. If it's 1, then it's an R-type instruction, and instruction 15 to 11 is sent to the right register. So when we combine these together, additionally, we're going to mention that the bit 15 to 0 is going to go past the registers because we're using that to indicate our immediate value. We're going to have it shifted. We're going to do sign extension to do 32 bits. So if when you get this value out and you're coding it, you have a 16-bit value. How would you sign extend it? Concatenate. Very good. And what are you concatenating? You have to make a decision. How do you know if it's a positive or negative number? So if the most significant bit is a 1, what do you do? What do you add on? What do you concatenate? 16 1. If it's 0, what do you concatenate on? 16 zeros. So it's just an if statement. If this, have your 32-bit value. If 1, do that. And then the next thing, we've been alluding to this quite a bit. We have this ALU op signal that's going to come out of the controller. If you remember from section 3 when we were talking about the arithmetic logic unit, and you had a 2-bit ALU op control signal and your function value coming in, right? And we made some decisions to calculate whether or not we're going to add or subtract or nor or shift left logic, set less than, or subtract, right? Subtract immediate. This is generated by our control signal. So it's a 2-bit control signal sent to the ALU control with a function from the instruction. So we have that 6-bit fucked, right? Which is used to determine the control signal input to the ALU, which is how many bits? How many bits is coming out of the, that's coming out of the ALU controller to go to the ALU, recall from section 3. How many bits? how many, okay, think about you did your ALU in project 1. And what was the size of the multiplexer that we needed to control the output? 16 to 1. And so how many control signals are used to control 16 to 1 mux? 4. That means 4 are going to come out of your ALU controller. The values coming out of that ALU controller are what are going into your ALU, which we designed earlier. And so when we tie all this together, this is what the second stage looks like. We come out of instruction memory. We have a 32-bit value. Instruction 31 to 26 goes to the controller. So on an exam, you can just do 31 to 26, and you can 25. You don't need to write instruction. It's coming out of instruction memory. You've demonstrated that enough. 25 to 21 always goes to read register 1, as we've described earlier. 20 to 16 always goes to read register 2. And then we split it off here. We have come to this multiplexer. 15 to 11 comes in here. We use register destination to decide whether or not we're going to use it. So if it's 0, we're using 20 to 16 to write. So what type of instruction is that? If we're writing from 20 to 16, so this would be RS, RT, and RD. So if I'm writing, so destination is RT, what type of instruction is it? I-type. Very good, I-type. And so if I'm using 15 to 11, what type of instruction is it? R-type. R-type. Very good. No, that's right. Very good. So then here's what we're doing next with this 15 to 0. We're using 15 to 11, but we're also splitting out 15 to 0 here. And then we're going to sign extend it like we just designed. And then from here, we're also taking 5 to 0, which is our function, and having it as an input to our ALU control, and a 2-bit ALU op, which is then going to control this 4-bit output, which we're going to go into in the next stage. Does this make sense so far? So we had our previous value that came from the program counter, and we have this magic value that's kind of coming out and holding our next instruction, which we'll go into in the next stage as well. So we're going to be, as you can see, we're kind of building up the data path to the final diagram. All right, so then your second assignment is to code this. So you already have your registers, you already have your 5 to 32 decoders, you already have your multiplexer, you already know how to sign extend, you already have your instruction memory. You've already done this in section 3. So you're golden. All right, so now we're in the execution stage. So we've taken everything out of our registers. So we've gone, to go back here, so we have our 5-bit values coming in, we translate it, we get our 32-bit values out. Now eventually, and we'll explain why. Okay, let me, because you might guys should know what's, so if you recall, there's a type of instruction where I have one value that I add. So I have 2 registers that I need to do it. I have a value that I add from one register, and I take the immediate value and I add it. But then that second register is a base pointer. So what are the 2 types of instructions that I need to do that? If I have a base pointer and an offset, what are the 2 instructions? You'll need to know it when you convert to C. So if I have a pointer, if I want either to store a pointer or load a pointer, what are my 2 instructions that I need? Store word and load word. Okay, so what's going to happen here is I have an arithmetic logic unit. I have a 32-bit immediate value here. And so I'm going to add these in the ALU. So what am I doing with the second value? So I've calculated my offset. And where do you think this value is going? So I have an offset and a base pointer. That's what I was hoping you guys would say. I have my base pointer here, and then they're going to go to data memory. So this is going to tell me what I need to do with this value. So that's why there's this little dangling line, kind of a preview of what's coming. All right, so execution stage, we're going to have this ALU source. So to come back here, we have this value coming here, and we have this value coming here. So if it's an R-type instruction, we need to add read data 1 and read data 2, because remember, recall the definition of a register type is you take two values from a register, perform some sort of operation, and store it back into a register, right? But an I-type, you're going to add, if it's an I-type, if it's add I, or load word, or store word, you're going to be adding using this extended value here. So you have to make some sort of decision. So what would you use here? I have two 32-bit values, and I need to make some sort of decision. What's the structure I want to use? Mux. Okay, now you guys are cooking with gas. Very good. So I have a 64 to 32 mux, which you've already done. And I need a control signal. And so we're going to call this ALU source. And so that's what the next topical guide objective is going to be. ALU source is used to differentiate between the read data 2 output from the registers and the sign extended instruction as the source for the second ALU input. If it's 0, it's going to be an R-type instruction. If it's 1, it's going to be using the immediate value. And I've also indicated here that the ALU also receives the 4-bit output from ALU control, and the 32-bit sign extended address is left shifted by 2, because now we're getting into byte addressing. So if you recall, we also use that immediate value for branching, right? And remember how I emphasized in this problem here that you're not going to want to multiply by 2 because it's physically coded into the data path. Remember that? So now I'm going to show you what I meant when I said this. So let me give people time to finish up writing this definition. Scroll up. All right, so what's going to happen here is we're going to get this program counter value, and we want to be able to maintain the program counter. So I told you how it kind of that looping back is just a placeholder. So we get the output, which is program counter here, and then we've hard coded 4 into this, right? So we have this value out, and what's going to happen is it's going to branch off, and we're going to be making some decisions later. Okay, so it looks like everybody has 7.6 done. So let me show you this is the add stage. So we have our instruction done. It's in the registers. We've written to the registers. We've sign extended. And here's what's going to happen. We have this value goes in here into the mux. And then read data 2 is also going to go into the mux. And as I've told you before, read data 2 is going to branch out and go along here. It is controlled by ALU source. Read data 1 always goes into the arithmetic logic unit. We have this 4-bit ALU operation, which has come out of our ALU controller. And then what's going to happen, and so this is where branching comes into play. We have a 32-bit value. It branches off. And then we're going to shift left 2. So you have a shift left logical that you've coded, correct? So you just hard code 2 into there. And then you have another adder. So you've taken, so in that problem that I gave you, let's say we wanted to branch 3 instructions, right? So the value that's in the immediate is going to be 3. Sign extended, still 3. Shift left 2, that means it's multiplied by 4, so now it's 12. We have this PC value. We've added 4, so we have the next instruction. So if you recall, I said find the value, add 1, and then that gives you the value that you want to branch by. So let's say I have my decision logic is instruction 6, and I want to skip 7, 8, and 9, and then 10. So here's why I do it this way. The adder here automatically adds 4 because I automatically want to go to the next instruction. So it's automatically going to go to 7. So if I need to get to 10, I need to branch past those instructions and get to 10. So that's why I add 3, not 4. So if you look in green sheet, that's why it says PC plus the instruction plus the number we want to branch by, because we're all automatically doing this. So the reason why I'm having you guys go over a little bit of section 7 before your exam 2 is because I hope that this makes why you're making those decisions on the C programming to assembly make more sense. Does that help out? Okay, good. So now we branch out because most of the time I just want to go to the next instruction, right? So I have the next instruction, which is this line here, as well as I've multiplied by 4 the number I want to branch. So I have PC plus 4 here, and then I have the branch value here. And so I have calculated the value and the ALU that I want. I have my 0 bit, because remember, we don't just automatically branch. We use that 0 bit to make the decision. So that 0 bit's going to come out somewhere. And that's going to be the next stage. So does this make sense? You guys aren't scared yet? Okay, good. And so for project 3, 7.3 is design the execution ALU stages defined in TGO 7.7. Okay, so I've alluded to this a little bit. I think this is a good contemporary issue. I told you we have all these codes that we code in. We have this arithmetic logic unit, and we've talked about signed and unsigned integers, right? So I talked about this game called Civilization. Okay, one person remembers. Okay, so this is another good, since you don't remember, you get to laugh again about it. All right, so the Atari used MOS technology 6502 CPU. And recall, I talked about this good design requires good compromise. It's an 8-bit video game system. So this is the actual chip that's doing. So in this section, we are actually designing this. So we have now that we've gone over the arithmetic logic unit, we can physically understand what happened in this video game. So the add and subtract immediate operations required 2 cycles, so it's performance, where it required an additional cycle to account for the carry bit in signed addition. So what happened was they were like, we want to get rid of this cycle, so we're going to make everything unsigned. But then we're just going to interpret it as a signed bit later. And they never thought about a specific type of addition. So what happened was, for each historical figure had an aggressiveness score, and they set Gandhi's score to be 1. And then they had an issue where if you became a democratic country, you subtracted 2 from your aggressiveness score. So Gandhi's aggressiveness score is supposed to be -1, but it's an unsigned integer. So what did it become? 55. So here's what happened in the video game. This is an actual screen cap. Okay, so I just described exactly what happened. And so I can zoom in here. And so Gandhi, he is now very, very aggressive and very bad. We will now mobilize our countries against you, and you'll pay with your foolish pride. And over here, it's like, greetings from Gandhi, ruler and king of the Indians. Our words are backed with nuclear weapons. So what physically happened was, went to the arithmetic logic unit. They were trying to improve for performance, trying to get rid of a cycle. But what ended up happening was they made Gandhi a genocidal maniac. So this is a fun little example of how what you're learning right now in class is applied. Okay, so this is why good design requires good compromise is important in light of make the common case fast. So you have to keep all of these things in mind when you're designing an advanced digital system. So now stage 4, we have data memory. So we have the ALU output, and we have our base address, and we have the value that we want to update, right? So in load word, we're taking this value, this 32-bit value, we're going to data memory, we're getting something, and we're loading it into a register. That value coming out of read data 2 is the physical value that's going to be coming back. So we're going to be using a multiplexer in the write back stage to differentiate between those two values. mem read and mem write. So remember in when we were designing registers how we had the SRAM control memory read and memory write? So in the instruction decode stage, you want to have your SRAM values automatically set to read and set write to 0. And what's going to happen is you're going to take that reg write value and come back at the write back stage, and then you're going to write either the result from the arithmetic logic unit or the result from data memory. And so in this stage, in 7.8, memory read and memory write, control signals are used to determine whether the information stored in data memory will be written to or read. And then branch, we're actually going to issue a control signal that tells us whether or not we actually want to branch. So if you're talking about before, we generate a 0 bit every single time. If you have a situation where you don't want to branch, but it generates a 0 bit, we don't want to branch. But if we have a condition where we might want to branch, but we don't generate the 0 bit, that means the branch condition wasn't met. So the only time I want to do this is if I have the 0 bit is 1, meaning that we've calculated it properly, and I have a branch control signal. So what logic structure, if I want to calculate, if I have 2 bit values, I have that 0 bit and my branch control signal, and I want them to make that branch selection if they're both, what's the logic value I want to use? What's the logic gate? And. Just use an AND gate. So that's what we're going to do. We're going to AND branch and 0 into a multiplexer, which takes in our PC plus 4 and our calculated branch address. And that's how we determine whether or not we want to branch. So a lot of these mem read, if you want to read from data memory, it's a 1. If you want to write to data memory, it's a 0. They're never the same. Just like Q never ever equals Q naught. Mem read and mem write are never both 1. They can be both 0. Especially if it's, what type of instruction would it be if I wanted them both to be 0? If I never wanted to read from data memory or write to data memory, I only want to deal with the registers. What type of instruction would that be? R type, yes, very good. So here is data memory stage. We have our sign extended value. It's come here. We have ALU source. We have our PC plus 4 comes into the adder. It circumvents. We have our output from the ALU is a 0 bit. We have an AND gate just as you designed. We have our branch control signal, which comes out of our controller. And that controls the signal line for a 64 to 32-bit multiplexer. And then I have here a decision between whether or not we just want to go to the next instruction or we want to branch. Now here, we have our arithmetic logic unit. Let's say we made the decision, let's say we did load word. So we calculated the offset, and we have our base address. We've calculated that value, and we now know our base address to the data memory. Now, if we are storing, we're doing a store word instruction, then what we want to do is we want to take read data 2, and we're taking that value from the register that we've calculated, and we're actually putting it here into this write data. This says write data. So we calculate our base pointer. We go to the place location in memory. We say mem write. And then we actually take this physical value and update that. So that's what's our pointer is physically being done. And so here's what a load word is. A load word is taking this value, we calculate the offset. We now have our base pointer and offset. We get our value. And then we're going to mem read, and then it's going to be out here, just like that. And then it's going to go back and write to the register that we indicated from our register destination, MUX. So that's how getting a pointer from memory, writing a pointer to memory, that's how it's done. if we're doing an R-type instruction, we're going to get this value here. We're going to read register 2. ALU source will be 0. And then the value will just go around data memory entirely over here. And again, if we want to calculate a branch, here's what happens. We take in read data 1. We take in read data 2. Where we have 2 register values. We perform the comparison. We get our 16-bit value of 32. We will sign shift left 2, which means we multiply by 4. We add PC plus 4. Branch is 1. 0-bit is going to be a 1. And then we now know our branch address. Okay, so it's 7.4, and then I want to go through right back, and this is where we'll conclude this particular portion of the lecture. We have 2 more control signals, jump and memory to register. Jump should be intuitive. It's a control signal used to determine if the instruction is a jump or not. 1 if it's a jump, 0 if not, and 12 memory to register. If we go back to this previous diagram, I have memory to reg determines whether or not I want to read from the memory or not. So either I have this value from ALU or memory. So I call the control signal memory to register. And many of you, when you do your final data path, will abbreviate as M2R. That is acceptable. So if it's determining if it's the memory register, that means I want the value for memory, which means this value, the control value, is going to be a 1, and this will be a 0. And this will go back to the registers. And so we'll finally define memory to reg as determines whether or the result from the ALU or the read data from read data memory is written to the determined register. And then I think this might be a good, let's stop at 7.12 because I do want to spend a good amount of time on this table. And then next lecture we will do the combinational logic. And then this is the combinational logic for the ALU controller. And then we will put everything together. Do you remember the first day of lecture I showed you that big diagram and I said, oh, this is big and scary, but by the time we get there, it'll make a lot of sense. So we're a day away. Does anybody have any questions before I dismiss you? All right, I'm going to